And off we go. We have to make an imine. That's what this first product is. So red first. Red first. And we got a lone pair. We don't need that lone pair. We need this lone pair. Second step, intramolecular proton transfer of this H. Change that to NH2 with a third H showing. We can draw that in blue. We're going to have to write the word intramole over there. Okay. Getting flashbacks to last week when I had to restart. Don't say that. Intermole for that last proton transfer. And looks like we have an R group we don't need to copy 100 times. Nitrogen has its lone pair back. Does what nitrogen often does with a lone pair, pushes it in, resonate, kick off a leaving group. And we have that species there. It's an iminium version of our imine. Ay. Sorry. Sound effects were not necessary. Plus charge. Hydroxide also generated. Deprotonate with hydroxide to your imine. And we have imine here. Hydride reduction. We've done so many of these were pros. I hope. Hydride. Attack the nitrogen, carbon, make the nitrogen anionic for step 2. R goes to anion, which needs to protonate using HCl. Giving us amine. Process going from here to the amine is called reductive amination. A to C, A, B, C, and A to C. Very useful way to make amines. That's why we had to review it. And then opening epoxides with a moderate or strong nucleophile. I got rid of one of the H's. Gonna do something like I did before. Attack. Generate an anion. My check mark's in the way. This check mark's annoying too. And attack. Not that carbon. Less hindered carbon. Yeah, the N is attached to a CH2 and we're done. Then the lone pair on the O minus, you just generated an O minus, will protonate from the amine. And believe it or not, it can reach this time. We have that extra carbon in the middle. Ring size as it goes and reaches is 5. You're going to have an N. Here, I'll count to 5. Watch. 1. Attached to carbon is 2. Attached to another carbon is 3. The O minus is attached to there's 4. That's 4th atom. The 5th atom in the ring during the transition state is a hydrogen. Ring size 5 during a transition state is perfectly acceptable. skipping right to here, we can just call this piece up here R double prime or R prime. It doesn't change. Exhaustive methylation. No doubt setting up a Hoffman elimination. And I can probably skip this part. I mean, we did one the other day. This is not a tricky one. So you get an NH. And C last week. Because then you neutralize it, and then you will attack another methyl iodide, and then you will, well, that'll be it after you attack the other methyl iodide. Just want to get more review in here. No, weeks don't make us feel weak. Some more than others do, but there we go. Weak. And I want to move on to that next one. Got an R prime and an R. No, it's a whole new ball game. I think you can review enamines on your own. I'm going to get rid of this page. It'll disappear. Because we had a request for a roadmap. We certainly don't have enough time to do the whole thing. Here's the Fall 19 T3 roadmap. Pick out some highlights. Students, oh, I like this. What's coming is better than what's gone. Very appropriate nowadays. So why don't we take this to this? Because we just talked about that. That part is called the exhaustive methylation, to put as many methyl groups on the nitrogen as possible. And I see hydroxide here. That's the next step towards a Hoffman elimination. So how do you get the methyls on there? Well, we did it here. We said, look at last week's notes right here. What chemicals got us from here? Sorry, here to here, and it was methyl iodide excess. So that's pretty easy. And that has a halogen up there. Okay, methyl iodide excess. Just remember that. We're doing this. CH3I excess. And then how do you convert the iodide and make it go away and get replaced by hydroxide? So you got to know the chemicals. The one that precipitates the iodide is silver ion. And to create the hydroxides, use silver oxide, and it's in water, so the water reacts with the oxide to make hydroxide. So that's how you set up a Hoffman elimination from an amine. Exhaustive methylation, silver oxide. It's silver with its normal oxidation state of +1. And then we got to figure out where our beta hydrogens are so we can do major minor alkenes. Remember, the nitrogen ammonium ions, the leaving group, which makes this a potential alpha, as well as this. Leaving groups are attached to alpha. Beta is one away. I think this will be minor after I take the beta H here. And I think this beta position will be major when I take this H away here. And the reason is this reaction is governed by steric hindrance. And this H is easier to approach. So my major alkene will be between alpha and beta. And let's just do it. And then we have that isobutyl here. We still have this bond to CH2, CH2C to an isopropyl. We didn't break this bond to make the major. There's the molecule. We took this H, made this into a pi, and this left, and that gives this result. Same story from the other side. Take this H, make a pi here. dimethylmethylene, CH2, CH2C, still attached to N this way. And this carbon has an isobutyl. Oh, and there's more oh, minor alkenes. Ooh. I think what I did, I don't know if it'll let me move this. Eh. And let me move this. And why do I think that's minor now instead of major? I realized I made a Z alkene. I could have made this E. Hello. Got to do this. This. Could have made the E. And E's a little more stable than Z. It has less steric hindrance. It involves removal of the same beta H, so that's not the story. And I think on the answer, I'm not 100% sure, but I think on the answer key, I can't do an EZ isomer of this one. I bet the answer key has this thing crossed off. I ran out of alkenamines because you can't do EZ isomer here. Okay. Oh my, such good apple. Interesting.
Professor?
Yes.
I have a question on the same page here.
Mm-hmm.
If you go up to the left, it's right here.
This
It's
one?
the benzene. No, just down a little bit.
This one?
To the right.
This one?
Yep.
Okay. How did we go from here to here?
Now how to go from there with the PBr3 and then aluminum chloride.
Oh, so PBr3 will convert this to a bromine, which makes that a secondary carbon with a leaving group. We're setting up for a Friedel-Crafts alkylation. We didn't call it Friedel-Crafts. It's just alkylation with a secondary carbon group with a leaving group, right? So a bromine goes here, and then aluminum chloride takes a secondary alkyl chloride, like just look at page 1 today, or page 2, because that's where we had the answers. How do you put a secondary carbon group on benzene? Carbon with a halogen, doesn't have to be chlorine, it can be bromine. And an aluminum chloride catalyst makes bond between the benzene and this carbon. So now we're talking about same story here. And close that up. And we're going to have a secondary carbon with a bromine here. And we're going to make a bond from here to what position on the benzene? Well, it really can't reach any position except for that one or that one. And in terms of steric hindrance, I'm favoring this one. I'll probably accept either answer here. I'm making a bond from this carbon to this here. Ring size will be 6 off the benzene. So you got your benzene, got your ethyl and your methyl, and your C to an N with an H. N with an H has a CH2C. And that makes her, it doesn't look pretty, does it? Is that ring size 6? Let's see. I'm going to go from here to here. Count them off. 1, 2, 3, 4, 5, 6. Do we have 6? We do have 6. It just looks funny. 1, 2, 3, 4, 5, 6. Yeah. And that's connected. And we have that. Any others on that page you want to look at?
No, but I just have a quick question on the retrosynthetic question.
The one we just did?
Yeah.
Coming back
segment.
up here. 2, 3. There it is. Yeah, there's many ways to do this, by the way. This is only one possible answer. The answer key has a different possible answer, I'm pretty sure.
So my question is, can I start by showing how I got the like if like I'm gonna start by adding like showing that this one, like the one with the carbon and then O and into the R group, it's a methyl, and then we added an R, an X and a halogen in that methyl, and then we did the Clemenson,
Okay, so
and then adding the other groups, the para and
you're
ortho.
talking about a carbon off of benzene that starts as just a CH3,
Mm-hmm.
and then you did a benzylic bromination or
So
something.
CH3, yeah, CH3 is gonna add ortho and para, right?
Yeah, exactly. So here, if you have a CH3, then what do you want to put on there?
So we can add the para one.
Yeah, so it can go some carbonyl group or something.
Mm-hmm.
Yeah, it'll go pair to that. I see a lot of advantages to this approach. And then you could do stuff from there.
Yeah.
You could do NBS and heat. This would be a nice way to get the ether on, by the way. And we're para. And you can go R O minus there. And this, I think I vocalized this idea and then I went against it because I had 2 allylic positions, which you solved by keeping the carbonyl. When I talked about it previously, I had a CH2 here and a CH3 here. So NBS is going to give you 50-50. I would have to deduct at least a half point. But the carbonyl won't suffer any reaction here with NBS. So this would be a nice way to make your ether. This would be an alternate strategy, wouldn't it? All right. I think, did we address what you wanted to talk about there?
Yes, thank you.
You're welcome. And then we'll just select some reactions here that maybe we want to look at, if it'll ever open. There it is. I think just nice little review going top of the screen here. Nitration. Yeah, you're putting a nitro group on benzene. Here's step 1. Nitro group goes on benzene. And then it's a meta director. It's the strongest meta director we have. So you're putting a carbonyl group, that's an acid halide there, meta to that. And then you're saying I have to reduce 2 things. I don't have a way of reducing this to a CH2 and NO2 to NH2. Nobody does. That's why there's 2 things here. So if you really love the lithium aluminum hydride, you better reduce this one first or else you're in trouble. Lithium aluminum hydride will take that and that, but it won't make this into what you want. Not this. It'll make an alcohol here. So you can avoid lithium aluminum hydride entirely. Do like H2 and nickel, and that'll take care of just the NO2. So there's your green H's there. And then you can do your Clemenson, but I suggest against it because this is now an amine, which is a base. A base reacts with acids in Clemenson, which is HCl. So I would go with the Wolff-Kishner myself. H2N, he's looking for a nice color. H2N, NH2, hydroxide, excess AQ, and that one does require heat. And that's hydroxide there. And without, let's just stay on the top, general review. Try to knock off all of these here. So how do you go from here to this? Well, you got a meta director here and an ortho para director here. Which one of them fits the bill? Because that's the one I want to put on first. If you put the para director on first, then the next group goes para, like I just said. I don't want that. If you put the meta director on first, then the next group goes meta, which is what I have. Put the meta director on first. Cl, carbonyl, and then propyl. Cl, carbonyl, propyl, and aluminum chloride. Don't forget that catalyst. That's a pretty bad looking 3. 3s and E's. That's what Starboard hates from me. What else? You got to put an isopropyl on there. Hey, why don't we do one of those show-off reactions? Yeah, you could use isopropyl chloride and aluminum chloride, or you could use something like this and H2SO4. That'll generate a secondary carbocation. Or you could use, or 2, here, just to show you what I was talking about. 2, you got the chlorine with the isopropyl and aluminum chloride. And you got that. And then going to the right, we're going to put a methyl on the benzene. What kind of a director is methyl on benzene? We'll draw that out. Methyl on benzene. Also known as toluene. Here's toluene. Step 1 gives us toluene. And where's the next group go? Para's major and ortho's minor. So toluene with an ortho NO2 group here. Minor. Para NO2 here. Major. Yeah, then the protocol that gets, this is 3 steps, guys. I don't know why I gave you only 2 in the box. You've got to first reduce the NO2 to NH2. Anytime you got to get rid of the NO2 group, first it's got to be an NH2. And we'll reduce that to NH2, H2 nickel. Then you have to diazotize it. NaNO2. HCl. AQ. Give you the bare minimum I need to see. Don't skip any of these pieces. 0 degrees Celsius. Yeah, you could add excess HCl. That's necessary, but I don't need to see that. And then how do you put a fluorine in the place of the N+N+ diazonium ion? That's the old HBF4. At 4 and room temperature. Room temperature, RT. And then how do I do this? The only change here is a bromine on the benzylic position. Here's the benzylic position in toluene. And that is our old friend, that bonus mechanism that you won't see. But it's a useful reaction for roadmaps for sure. Benzylic halogenation, or allylic if you want that. But given that chapter 21 and 22 aromatics, we're probably doing benzylic. We're going to make a good old Grignard. Oh, let's carry on. Well, we have done everything from here, first step. And we got 5 minutes. Let's use them. How do you make this guy here? Called anthranilic acid, by the way. You don't need to know that. It's oxidizing a methyl to a carboxylic acid. That is the end of chapter 21. You have to generate chromic acid first in the ways we've done for 2 semesters running now. There's one of the 2 ways. And then you must, this is where if you skip the heat, I got to give you trouble. This reaction requires quite a bit of heat. So oxidation of a primary, any benzylic carbon that has an H gives us this result. And this is the diazonium species here. There's a triple bond between the N and the N. And we really need to know that protocol. It shows up everywhere. NaNO2 HClAq. Don't stop. Temperature. 0 degrees Celsius. Don't want that thing breaking down on us. Oh, this is a diazonium di here. And the nucleophile was here. Here's the new. We've already got this piece. And the lone pair on the oxygen is what makes this a nucleophile. And you just copy everything I circled there. That's it. It's a beta methoxynaphthalene. What? That's what it is. Beta methoxynaphthalene. There's alpha right there, and there's beta there. And room temperature. And that does a diazonium species. Don't know which one that is. We may have invented a dye there. Good review here. Magnesium diethyl ether. Take us to the start of the semester. Make a Grignard right there. Grignard's attack right here on the less hindered part of an epoxide. And HCl is going to give us an OH instead of an O minus. So without further ado, NO2, CH2 with an exciting new bond to CH2 carbon that has a diethyl here and an OH. And I bet we're closing up a ring down here. Yeah, it seems to be a favorite thing of mine, doesn't it? If I can generate a cation here, and yes, our very first thing today, we reminded each other that from a tertiary alcohol, you can make a cation as long as you put a strong acid in there. Sulfuric, toluene sulfonic will do the job, and cation generates, and electrophilic aromatic substitution ensues. And what about here? Bromine and iron. There's clue here. Where's the new group down here? Oh, it's down here. This is a more powerful director than fluorine. Pair is already taken. Ortho's next best. And yeah, we're closing up here because it's time to close.
Professor, can you please check your email?
Uh-oh. Is it something that
no,
take care of off air?
No.
Okay, I'll check my email for sure.
Thank you.
It's yeah, we got a fluorine here and our new bromine ortho to our methyl. And it looks like we're going to make a Grignard and open up another epoxide here. But anyway, you've got the answer key to that. I'll be posting everything later today and checking my email right now. So I'll see you guys. Don't forget, Wednesday is our test. I'll send you some more information as we get closer. And adios.